Hello there, Mr. Sutton with the AB Calculus 6-2 Extra Practice Number 1 Solutions on differential equations with separable variables. For this problem, at each point on a certain curve, the slope of the curve is 3x squared y. If the curve contains the point 0,8, then what is its equation? So this is essentially a differential equations kind of problem in disguise. If we're saying the slope of the curve is this, we're essentially saying dy over dx equals 3x squared y, which means we need to solve this for its particular solution that has the initial point, the initial value of 0,8. All right, well, I noticed that we have a y in our differential equation, so we're going to have to use separation of variables here. So I'm going to start by dividing y to the other side, so I have dy over y, and then I'm going to multiply both sides by dx, so 3x squared dx. Next, I'm going to take the antiderivative of both sides. On the left, we've got ln absolute value of y. On the right side, this bumps up to a 3. Dividing by that, we have x cubed plus c. Now to use my initial condition of 0,8. So on the left side, I have ln of 8. And on the right side, this is 0 cubed plus c, which is just c. So then essentially, c equals ln of 8. And we don't really need that absolute value anymore. All right, time to plug that back in to the general formula to get the particular solution. But before we do that, let's resolve this absolute value here. Since y initially is 8, that means that the y in this absolute value is greater than 0, which means that we do not need the absolute value anymore. So I can just write ln of y equals x cubed, and now I'll just add in my c value of ln of 8. Next, we have to isolate y, so we're almost there. We'll just raise e to both sides. So I have y equals e to the all of this stuff. And I said we're almost there, but you'll notice this is not in any of the answer choices. That's because this ln of 8 can actually be split off. We can say e to the x cubed times e to the ln of 8. And e to the ln of 8, of course, is just 8. So we can rewrite this as 8 e to the x cubed. And that's going to give us, let's see, answer choice A. For this problem, we want the particular solution to this differential equation with this initial condition. So let's go ahead and separate our variables, and then we can take the antiderivative. We need separation of variables because we've got y, the output variable, in the differential equation. So my first step, I'm going to divide both sides by y squared to get it with dy. So I've got dy over y squared, or y to the negative 2 dy, either way. Then I'm going to multiply both sides by dx. So that gets it over to the right side with the x. Next, it's time to take the antiderivative. So this exponent bumps up to a negative 1. Dividing by that, we have negative y to the negative 1. And on the right side, this will be 1/2 x squared plus c. Using my initial condition now, on the left side, I've got negative 1 to the negative 1. And then on the right side, I have 1/2 of 2 squared plus c. So on the left, this is just negative 1. On the right side, this is half of 4, which is 2 plus c. Negative 1 minus the 2 over here gives us a c value of negative 3. All right, it's time to plug that back into the general solution. So I have negative, we'll call this 1 over y because we're going to need to do some stuff with it anyway, equals 1/2 x squared minus 3. Now we have to isolate y. I'm going to start by multiplying everything by, actually, no, I take that back. I was about to multiply everything by 2 or negative 1 or something like that. But first, I think I'll actually move these together into one big fraction. And the reason I'm doing this is I'm looking at the answer choices, and I'm noticing there's a lot of things that only have one fraction in them. So let me just merge these together. So I need a common denominator of 2. That'll make this 3 into a 6, so I'll have x squared minus 6 over 2. Now I'm going to isolate y a little bit more now. So I'm going to multiply everything by a negative. So that gives me positive 1 over y on the left. And on the right side, I'm just going to multiply the negative 1 by the numerator here. So I've got negative x squared plus 6. Or you can write it as 6 minus x squared. Next, I'm just going to flip both sides. So I have y equals 2 over 6 minus x squared. And that's going to be, let's see here, 2 over 6 minus, there we go, d. For this problem, we're trying to find the particular solution, although they don't say the word particular, to this differential equation with our initial condition down here. So for our first step, I noticed that I've got a y in the differential equation, which means I need to use separation of variables to make this happen. And how can I separate the variables? Because they're both kind of stuck in the exponent here. Well, if I have two things being added in exponent land, that means that I can kind of unsimplify this into two bases that are being multiplied by each other. I can rewrite this as e to the y times e to the x. And now I can separate my variables. So I'm going to divide both sides by e to the y to get it over with the dy. And I'll actually write this as e to the negative y because it's a little bit easier to use my reverse power rule in that situation, or my exponent anti-differentiation rule. And now e to the x can stay where it is, and I'll multiply both sides by dx to get it over on the right side. Antiderivative time. On the left, we've got negative e to the negative y. On the right side, this is even easier. No pun intended. We just have e to the x plus c. Won't get any easier than that. Initial condition now. We're going to plug in 0 for x and negative ln of 4 for y. So on the left side, I have negative e to the negative ln of 4, which I can just call that the ln of 4 in a minute. On the right side, I've got just e to the 0 plus c. So on the left side, e to the ln of 4 is going to be 4, and there's a negative out in front, so that's negative 4. On the right side, we have 1 plus c. Negative 4 minus 1 is going to give us negative 5 for our c value. Plugging that back in our general solution, we have negative e to the negative y equals e to the x minus 5 now, and it's time to go ahead and try to isolate the y value. I'm going to have to start by multiplying or dividing everything by negative 1. So I'll have e to the negative y on the left and 5 minus e to the x, or negative e to the x plus 5, either way, on the right side. Next, I am going to take the ln of both sides to get this y out of exponent land. So I'll end up with negative y equals ln of all the stuff on the right side here. And finally, I'll multiply both sides by negative 1 to get y completely by itself. So then negative ln of negative e to the x plus 5 would be our final answer, and that matches up with choice C. For this problem, if dy over dx equals x squared y, then y could be, so this is kind of interesting. They're asking essentially for a particular solution to a differential equation, but they're not giving us an initial condition. So we're going to have to kind of roll with this and just pick the best answer. All right, so let's at least start by getting our general solution. Now I notice I have a y in the differential equation, an output variable, so that means I need to separate my variables. I'll start by dividing both sides by y, so I have dy over y, or 1 over y times dy, either way. On the right side now, I'm going to multiply by dx to get it over to the right, so I've got x squared dx. And now for my antiderivatives on each side. Left side, we've got ln absolute value of y. On the right side, this bumps up to a 3. Divide by that, so that's 1/3 x to the 3rd. And then plus c, don't forget that. All right, now we don't have an initial condition, but I need to isolate y at some point if I'm going to get some kind of particular solution. So let me try doing that. And let me assume for our purposes here that y is positive. And the reason I'm assuming that is because looking in my answer choices, I don't see anything negative. So if this ended up being a negative y, it would have carried over to the end of the problem. So let's assume this is positive just based on the answer choices. So I'm going to raise e to both sides then to get rid of this ln. That gives me y equals e to the all the stuff on the right side. And at this point, I need to match it with one of the answer choices. I don't see any of the answer choices that really look quite like this. Unless we're assuming that C was 0, then it would kind of match up with choice B. But then we have this plus 7 out here, and there's no reason to believe there's a plus 7. The plus C is in the exponent, not free-floating here as a separate term. So what else can we do? Well, I know that if I have addition in exponent land, I can split that up with two bases. So I can take out this C and make like a separate e to the c that's being multiplied by the first e, and now I've split those up. And this e to the c, I don't really know exactly what it is because I don't know what c is, but we can think of this e to the c as kind of its own constant. So I can think of this really as being just y equals k e to the x cubed over 3, or pick whatever letter you want to represent your favorite constant. So I basically have the pattern of something times e to the x cubed over 3. Let me see if I can find that in the answer choices. So not A, not B, again, because we have this plus 7 over here, so that seems to rule that one out. C looks like a pretty good candidate if this k value is 2. And then D doesn't have the right exponent. E doesn't even have, really, an exponential function. So C is our best answer here. On this problem, we're given the differential equation shown up here, and we want the particular solution if we have an initial condition of f of 0 equals 3. All right, so let's go ahead and start this one. Now, I notice we have a y in the differential equation, an output variable, so I need to separate my variables to do this one. I'm going to start by dividing dy by y minus 1, and dy over y minus 1 is going to equal, now on the right side we're going to have x squared times the dx that I'm moving over there. And now it's time for some antiderivatives. On the left we have the ln of absolute value of y minus 1. On the right side, this exponent bumps up to a 3. Dividing by that, I have 1/3 x cubed plus c. And now it's time for my initial condition to be plugged in so I can find that c value. So on the left, I've got ln of absolute value y minus 1. Let's see, y is 3, so that's going to be 3 minus 1 over there. And then on the right side, we have 1/3 times 0 cubed plus c. Well, that zeroes out that term on the right side, so I just have c on the right side. On the left side, I just have ln of 2, so then c must have a value of ln of 2. I'll plug that back in for here in a minute, but first let me figure out what I'm doing with this absolute value, because we can't just leave it like that. Now, I notice I have an initial y value of 3. So if y equals 3, then this y minus 1 stuff in here is going to come out positive, which means I don't need the absolute value. I don't need to negate anything. I can just replace this with a parentheses. So I'm going to write ln parentheses y minus 1 equals, we have the 1/3 x cubed still, plus our c value of ln of 2. All I need to do now is isolate y. So I'm going to start by raising e to both sides. That gives me y minus 1 on the left and e to all this stuff on the right side. Now, I'm going to clean up my right side a little bit. It's not really necessary, but I just like to make things neat and clean. So when you have one of these plus ln's in an exponential term here, we could split off this ln of 2 into a separate base exponent combination. We could call this e to the this stuff times e to the ln of 2. E to the ln of 2 is just 2, so I could really just write this right side as 2 e to the 1/3 x cubed. Not necessary, but they usually do it in the multiple choice part. Now I just have to add the 1 over there and call it a day. On this problem, I'm given this differential equation, and I want to find the particular solution, essentially, with an initial condition of 6, -4. Now I notice I have a y in the differential equation, so I need to separate my variables if I have an output variable hanging around in there. I'll start by multiplying y to the other side, so that's y times dy on the left, and I'll multiply dx over to the right side, so I have 3 minus x quantity times dx. Now it's time for some antiderivatives. On the left, we've got 1/2 y squared. On the right, this is going to be 3x minus 1/2 x squared plus c. And now I'm going to plug in my initial condition to figure out the c value. So on the left, I have 1/2 times -4 squared. On the right side, I've got 3 times 6 minus 1/2 times 6 squared plus c. So I've got some number crunching to do here. Back on the left side, we've essentially got half of 16, which is 8. On the right side, this is 18 minus half of 36. Well, half of 36 is also 18. So essentially, these are canceling out, and we just end up with c equals 8. It's nice how it always seems to work out neatly like that. All right, now we can plug this back in. There's nothing to really resolve in this general formula here, this general solution. So just plug in 8 for c, and I'll do that over here. And all that's left to do is isolate y. So I can start by multiplying everything by 2. That gives me y squared equals 6x minus x squared plus 16. And then I need to square root both sides to get y by itself. But now we can't have a plus or minus square root, so I need to figure out, is y positive or negative? Looking back at my initial condition here, it says essentially we have a y value of negative 4. So that means y must be negative then when we take the square root here. And we're going to end up writing y equals the negative square root of all that stuff. For this problem, we're given a differentiable function f, and f's derivative right here, 4 minus x times x to the negative third, x greater than 0. First part, we want to find the x-coordinate of the critical point of f, so apparently there's only one, and then figure out if it's a max, min, or neither, with justification. All right, so if we want to know about critical points, we need to figure out where this f prime is either 0 or undefined. So I'm going to start by just setting it equal to 0 and see where it at least meets that condition. We see very clearly here, since it's already in factored form, that if we plug in 4 here, we're going to zero out the whole thing. So this thing equals 0 at x equals 4. Now, we can't get a 0 out of this x to the negative 3. This is really 1 over x cubed, but this function is undefined at x equals 0, so that's actually a critical value too. However, even though we don't exist at x equals 3, we're only asking about x values that are greater than 0, because that's what they set up here, x greater than 0. All right, so let's go ahead and if I'm looking to see if this is a max, min, or neither, I can use my first derivative test. So I'll set up a number line. This is an f prime line. And I've got 0 over here because I don't want to look at anything to the left of 0. But I've also got 4 as my critical value. So I'm going to test some numbers here. Between 0 and 4, I'm going to test 1. And if I plug 1 in here, I've got a positive times a positive, so the whole thing is positive. If I test something bigger than 4, like 5, well, this parentheses comes out negative. The x to the negative 3 still comes out positive, so that's a negative overall result. I see here that f prime is changing from positive to negative at x equals 4. Therefore, f has a relative max at x equals 4. Now, we also could have used the second derivative test here, but that would have required finding the second derivative, and we're not going to do that any sooner than we have to. Well, speak of the second derivative, and it appears. We need to find all intervals on the graph where f is concave down. Well, yeah, now we need the second derivative. So let's go ahead and find that. F double prime, we're going to have to use the product rule for this one because we have a product. So I've got u prime v minus uv prime as a general guide, but I don't really get anything just for writing this. I actually have to find them. So I'll use my box over here. We've got 4 minus x and x to the negative third, and their derivatives, which are negative 1. And this is going to be negative 3x to the negative 4, subtracting 1 from the exponent. Now let me go ahead and actually multiply this out, because to figure out concavity, I need to figure out where this second derivative is positive or negative, which means I need critical values for it, which means I need to actually put it all together and find the zeros. All right, so doing my ribbon here, I've got negative x to the negative 3, and then going the other way, distributing, we've got 4 times this, so that's going to be negative 12x to the negative 4th, and then we have negative x times this, giving us positive 3x to the negative 3rd. Just to make my life a little easier, I'll collect my like terms here. So we have a negative and a 3, negative 1 and a 3 of x to the negative 3rd. That's going to be 2x to the negative 3rd. All right, so this is what I need to find critical values for. And we already can see right away that we're going to have a critical value at 0, because these are really 2 over x to the 3rd and 12 over x to the 4th. But we don't really care about if 0 is a critical value, because again, this is only applying for x greater than 0, so that kind of limits us. But I am going to find the zeros for this function. So to do that, I'm going to put it in fraction form like I've done here, and I can turn these into not fractions by multiplying by the LCD, which happens to be x to the 4th in this case. Multiplying everything by x to the 4th, I've got 2x for this first term minus 12 equals 0. And here we can see if we add 12 and divide by 2, we have x equals 6 as a critical value for this. Well, let me make a number line for this. So this is an f double prime line now. We're starting at 0, and we have a critical value at 6. plugging in something between 0 and 6, like 1 is kind of my go-to here. 2 times 1 minus 12 is negative. If I plug in something bigger than 6, like 7, 2 times 7 minus 12 is going to come out positive. Now, I wanted to figure out where my graph was concave down. That means I'm looking for places where the second derivative is negative. So for my justification, I can say that f double prime is less than 0, negative, on the interval from 0 to 6. Therefore, f is concave down on 0 to 6. For this problem, we want the function f given that f of 1 equals 2. So this is kind of a differential equation sort of problem. I mean, we basically have dy over dx here equals this stuff, and this is your initial condition right here. So I'm going to do the Diffie-Q dance on this, which means I need the antiderivative of f prime. To get that, before you freak out about how you've got these things being multiplied, why don't we just distribute this x to the negative 3? So I'm going to rewrite this as f prime equals 4x to the negative 3 minus x to the negative 2. And this is a fairly straightforward antiderivative now going left to right here. So I can write f of x equals, and here this is going to bump up to a negative 2. Dividing by that, I've got negative 2x to the negative 2. This next one bumps up to a negative 1. Dividing by that, I've got plus x to the negative 1. Don't forget the plus c. And now we'll just plug in our initial condition here to figure out the c value. So this f of x equals 2 when x equals 1. So I'll plug in 1 for all the x's here. And going through here, let's see here. This is just really negative 2. This is just positive 1. Negative 2 plus 1 is negative 1. If we add 1 to the other side to cancel out that negative 1, we have 3. So c equals 3. And then we only have really one more step here because there was no absolute value or anything else to resolve. We just have to plug 3 in for c. So negative 2x to the negative 2 plus x to the negative 1 plus 3, that is our f function.